So in this section, we're going to focus on reaction stoichiometry. I know I've used this word stoichiometry before. It's kind of like complex dimensional analysis, I guess. We are converting from one unit to another, but we're specifically converting within the confines of a balanced chemical reaction. So stoichiometry involves using the coefficients in a balanced chemical equation to determine the quantities in chemical reactions. Basically, we can say we're going to react this much of our product, or this much reactant, how much product can we make? Or I really need this much product in the end, how much reactant do I need to be able to make this much product? And it's just kind of going back and forth and comparing those pieces. Now, we do need a balanced equation here because it's the coefficients that are going to tell us how many of one thing react with how many of another thing to produce how many things of what we want. Basically, that balanced chemical equation is what's going to allow us to compare apples to apples instead of apples to oranges. So for an example here, we have solid aluminum reacting with hydrochloric acid, forming an aqueous solution of aluminum chloride and hydrogen gas. Putting that into words, solid aluminum is Al, aluminum is the elemental symbol, and that lowercase s for the phase. I know that does not maybe look like a lowercase s, I swear that's my lowercase s's. Hydrochloric acid is HCl. To form is telling me I'm now separating my reactants and my products. Aqueous solution, aqueous is telling me my phase. Aluminum chloride. You guys should know that aluminum chloride is AlCl3 because aluminum is always 3 plus, chloride is always -1. So to neutralize that charge there, I need to have 3 chlorides for every 1 aluminum. And we know it's an aqueous solution. And hydrogen gas. Hydrogen is one of our diatomics, so we do have H2 here. So this is what I have written here. But now I need to balance this. Why do I need to balance it? Again, a balanced reaction tells us what is reacting and how many of each species is involved. Again, we need to compare apples to apples. So we have to balance this. When we look at this, you can do the counting of the atoms method. We've got, and you can write that out if, I recommend writing it out until you're comfortable and can do this faster. So on my reactant side right now, I have 1 aluminum. On my product side, I have 1 aluminum. On my reactant side, I have 1 hydrogen, and on my product side, I have 2 hydrogens. On my reactant side, I have 1 chlorine, and on my product side, I have 3 chlorines. So it doesn't really matter where I start here, to be honest. I'm going to go ahead and balance my chlorides first, my hydrogens first, so because that's going to affect the rest of my reaction. Some of that just comes from training, and you'll become more intuitive with that as you practice more. But I'm going to balance my hydrogens first on my reactant side to my product because that's going to affect my chlorides. So I'm going to say 2 HCl's. That's going to change this to a 2 here, and that's going to change this to a 2 as well. So now I need to balance my chlorides. I see I have 2 on one side and 3 on the other. That's clearly not going to work. The easiest thing to do there is to make it the lowest number multiply. I don't remember what it's called in math anymore. It's been so long. Basically, multiply the 2 by each other. You're going to get 6, and it's going to balance them all across. So I'm going to turn this to a 6, and I'm going to multiply this by 2. That's going to give me 6 here, 6 here, 6 here, and 2 aluminums. So now, let me clean this up just a little bit. Now, with my most recent work, I have 2 aluminums on my product side, 6 chlorides on my product side, 6 hydrogens on my reactant side, and 6 chlorides on my reactant side. So next I need to rebalance my hydrogens. I'm going to put a 3 in front of there. Now my hydrogens are balanced. Now all I need to do is balance out my aluminums. I'm going to multiply it by 2. And since it's just aluminum there, it doesn't affect anything else. That's how we get the 2, 6, 2, 3 ratio we have going on here. So this reaction, or this equation, reads as 2 moles of solid aluminum react with 6 moles of hydrochloric acid to form 2 moles of aluminum chloride aqueous solution and 3 moles of hydrogen gas. Let's go ahead and I'm going to write that out. If you need something from this slide, though, I would write it down now because I don't have a lot of room. Because one day I hope to be back on a whiteboard, a true whiteboard, and so I don't have a lot of room on the slide to write this out. But I'm going to write it up here. So this is telling me that 2 moles of aluminum, solid phase, reacts, or you could say solid aluminum, reacts with 6 moles of hydrochloric acid. HCl aqueous means acid. I'm just not writing it out the whole word, but you should write out hydrochloric acid to produce, or to form and to produce mean the same thing, 2 moles of aluminum chloride, aqueous, and 3 moles of hydrogen gas. So it's telling me the number of moles. It also means that if I just had individual atoms, it means 2 atoms of solid aluminum have to react with 6 atoms of hydrochloric acid, and that will produce 2 atoms of aluminum chloride and 3 molecules of H2. From this, we can derive those mole-to-mole ratios. So again, rewriting what I wrote above, let me actually just put it onto words, so I know sometimes students like to see in the full words instead. 2 moles of solid aluminum react with 6 moles of hydrochloric acid Again, I know it's hydrochloric acid, and I specify that by putting this AQ symbol. AQ means aqueous, and that's what acids will be. If I put HCl gas, that would be molecular. That would be a gas molecule, not an acid. To make hydrochloric acid, we actually bubble HCl gas through water, and it dissolves it in the, it kind of dissolves the gas in the water itself, and that's what makes the hydrochloric acid. To produce hydrochloric acid, or reacts with hydrochloric acid to produce 2 moles of aqueous aluminum chloride and 3 moles of gaseous molecular hydrogen. Now you see why I like the balanced equation. This little piece right here was a lot faster to write than all of that nonsense. Plus, my writing got messy. I ran out of space. Much easier to write a balanced equation. So I love this meme here. One does not simply do stoichiometry without converting to moles. That is incredibly accurate. And we're going to see that in the example soon. But no matter what you do, if you are doing stoichiometry, make sure you convert to moles. We must have everything in moles. We cannot compare grams to grams because remember, the weight of something is dependent upon the number of protons, neutrons, and electrons it has. That does not mean that 1 gram of oxygen reacts with 1 gram of hydrogen. Those are different amounts of how much hydrogen and oxygen I have. 1 gram of hydrogen is about 1 mole of hydrogen by itself, not diatomic or molecular hydrogen, but 1 mole of hydrogen weighs about 1 gram. 1 mole of oxygen weighs 16 grams. So 1 gram of oxygen is about 1/16 of a mole of oxygen atoms. It's not the same thing. So we have to compare mole to mole. And again, here we can now derive our mole. So the other thing we need to talk about here, though, is these mole to mole ratios. We can derive mole to mole ratios. So we talked about how, 2 moles of aluminum, solid aluminum, are going to react with 6 moles of aqueous hydrochloric acid to be able to produce or form 2 moles of aqueous aluminum chloride and 3 moles of hydrogen gas. But we can also derive mole to mole ratios that we're going to use in our stoichiometry. So looking at the balanced equation here, we're focusing here. This equation tells me that 2 moles of aluminum reacts with 6 moles of HCl. It is a complete conversion there because it's 2 moles of aluminum reacting with 6 moles of HCl. But I can also write that as 2 moles of aluminum divided by 6 moles of HCl because this equals 1. Because they're equal to each other, the one divided by the other also equals 1. I have to write the word mole there. We have to specify we're talking about moles here because we could be using other units, so you do need to specify mole. And you could also write it as 6 moles of HCl divided by 2 moles of aluminum. So either one can be on the numerator. We could say 6 moles of HCl to 2 moles of aluminum chloride. We could say 2 moles of aluminum chloride to 3 moles of H2. We could say 3 moles of H2 to 2 moles of aluminum. We could say 2 moles of aluminum to 2 moles of aluminum chloride. And that's not all of them, there are a few more, but you see the reasoning behind this is all of this balanced equation gives me is these multiple ratios. These multiple ratios are what I'm going to use in my stoichiometry step. The coefficients here are what tells me how much of one reacts with how much of another, and that's what I need to move forward. So here, I do have it written as equation. I apologize, I was recording, and of course the sound stopped recording, so I have to redo part of the video. But the coefficients give the reaction, which you can also call equation. I call it reaction because I think about things reacting, but it is technically a balanced equation. They give you the recipe in moles. They become the multiple ratios and are used as your conversion factors. So these coefficients show us our multiple ratios. You can compare moles to moles, liters of gas to liters of gas under similar or specific conditions, or molecules to molecules. We cannot, under any circumstances, compare masses to masses because, again, they do not combine in terms of masses. I know I said this in the previous slide, but if we had 1 gram of hydrogen and 1 gram of oxygen, 1 gram of hydrogen is about 1 mole of atomic hydrogen. 1 gram of oxygen is about 1/16 of a mole of atomic oxygen. They're not going to react the same way. It's not a comparable reaction. So note the coefficients do not affect your molar masses. The molar mass is still the mass of 1 mole of a pure substance. What we do is we take that molar ratio and we multiply it by whatever we're given, whether it be grams, moles of a species. We're going to do some examples, show you in a sec how we can get through that. That molar ratio is still correct. We're just going to figure out how much of a fraction, either greater than or less than 1, do we have compared to that mole ratio or molar mass ratio that we're going to be using. So these are some steps I want you to follow when you're doing these reactions. First, I don't have it written down here, but the first thing I want you to do is write down, what do I want to know? I want you to think about this question all the time. What do I want to know? This question is probably going to lead you the best this entire course. What am I trying to decide here? What do I want to figure out? So first, you do need to recognize that you need to use stoic when the example gives you information about one or more of the chemical species in the reaction and asks you about a different chemical species. What does that mean? Well, it's all about context. I talked about that in a previous video about how in the English language, we use context a lot to figure out what we're really trying to say. We have a lot of words that are spelled the exact same, but they have different meanings and they're pronounced differently. And we use context to figure out what we're talking about and what we mean. It's the same thing in chemistry. We have to read into the context of the question. It's not always explicitly stated, but through studying, through practicing, through working problems, you'll be able to pick up that context as well. So when you need to use stoichiometry, if you're given information about one or more of the chemical species that's reacting or being produced and ask you about something else. So for example, I say, how much of this can I produce how much of, product A can I produce if I'm got 10 grams of reactant A? Well, that's stoichiometry. If I have this much of this reactant, how much product can I make? That's stoichiometry. We're trying to convert between products and reactants. You can convert between reactants themselves too. If I have this much reactant, how much of the other reactant do I need to completely react all of this species? That can happen too. We're going to deal with it in gases. We're going to deal with it in energy. So we're going to see stoichiometry come through a lot in this semester. In order to do stoic, you must, no exceptions, have a balanced chemical equation. We need the mole-to-mole ratios of the species involved. The only way to get mole-to-mole ratios is to have that balanced equation. So first, think about what you want to know. But from there, you're going to change your given quantity into moles. So whatever you're given, whether that be grams, if it's already in moles, you don't have to convert. Grams, liters, milliliters, whatever you need, we're going to figure out how to get to moles. From there, you're going to use your mole-to-mole ratio to convert between different species. And then once you've done that, got to the correct species you want, you can take down moles and convert back to the answer you desire. We're going to do 3 examples here showing you how this is. So example 1, how many moles of oxygen will be produced by the decomposition of 5.8 moles of water? So when you get a question like this, the first thing I want you to do is go through and highlight. I highly recommend bringing highlighter to your quizzes and exams. Students did it in my summer class in Gen Chem 2, and one person started it. We talked about the success of it, and by the end, a lot of the students were doing it, and they actually do a lot better. So I highly recommend that you bring a highlighter to highlight through the question what's important. I also recommend you take your quizzes and exams in pencil, not pen, but I realize some of you are not going to ever write in pencil. It's just, you guys scribble all over, and it's hard to see sometimes what you guys are trying to do. Anyway, that's a moot point. I want to know how many moles of oxygen specifically, will be produced by the decomposition of 5.8 moles of water. I see I am given my balanced equation here. Make sure it's balanced. I've got 4 hydrogen on each side of the reaction, 2 oxygen on each side of the reaction. So it is in fact balanced. I'm going to write down, what do I want to know? I want to know the number of moles of O2. Remember, when it says moles of oxygen, that means O2. If I meant a single oxygen, I would either get that from context or I would say atomic oxygen. But oxygen being produced is going to produce O2, not just O. Plus, I see it in my balanced equation. By the decomposition of 5.8 moles of water. So I want to know the number of moles of O2 that's going to be produced if I start with 5.8 moles of water. Now, the first step is to change your given quantity to moles. I don't have to, it's already there. So step 1 is done. Our second step is to use the mole-to-mole ratio to convert to the moles of the new species. Okay, I've got 5.8 moles of water. Based on my balanced equation, I know that 1 mole of O2 is produced for every 2 moles of H2O that's decomposed. Until you are very good at this, or possibly forever, because I still do it sometimes, I recommend that you make sure your units are canceling. So make sure mole of water is canceling out. Remember, something in the numerator and something in the denominator is what's going to cancel out there. This will help, if you cancel these out like this, it will help keep you on track to make sure that you're actually putting this in the right order. Because again, you could write this as 1 mole of O2 divided by 2 moles of H2O. But you could also write this as 2 moles of H2O to 1 mole of O2. They're equal to each other. They're both equal to 1. And students will often write them backwards. So I recommend making sure your units are canceling so that you don't write them backwards. Remember, just because I'm canceling units does not mean that I'm canceling numbers. These numbers are still very prevalent and very important to keep in here. So do not cancel out your numbers. Complete the calculation. 5.8 times 1 divided by 2 gives me 2.9 moles of O2. This means that if I decomposed 5.8 moles of water, I would produce 2.9 moles of O2. So this molar ratio here is what's going to deal with the ratio of the species to each other. This is how much I'm actually starting with. This is why I don't have to use just 1 mole of something. If I had exactly 1 mole, well, I wouldn't care so much about stoichiometry. I could probably do it really quickly in my head. But in stoichiometry, we're not using just 1 mole of something that we're reacting or producing. We're always going to have these weird numbers, and it's going to be some percentage that we can compare to the original number, the original ratio here, but that gets corrected for it in the math. So 5.8 moles of water decomposed will produce 2.9 moles of O2. Okay, what mass of hydrogen gas, so I want to know mass of hydrogen gas, can be formed if 12 grams of aluminum reacts with excess HCl? When it says mass here, it doesn't specify, but it means grams. Mass means grams, okay? The other thing I like to do is I like to write down below the equation what I have. So I'm told that I'm reacting 12 grams of aluminum with excess HCl, and I want to know the number of grams of H2 produced. What do I mean by excess HCl? When you have more than one reactant, one of those reactants is going to limit how much product you can produce because it's going to run out. If I have 12 grams of aluminum, only 12 grams of aluminum can react until there's no more aluminum present. Now for HCl, if it had told me a specific amount for HCl as well, I would have a limiting reactant problem, which we will do in another video, but in this chapter. But in this case, what this means by saying excess HCl is that I have more than enough HCl to react all of the aluminum present. That means that the amount of aluminum I have is what's going to limit how much H2 I can actually produce. So write down what you want to know. You want to know number of grams of hydrogen. Hydrogen gas is a diatomic, so you need to remember that, plus it's in the balanced equation that way. But it is a diatomic, so you do need to remember that it's H2, not just H. I'm starting with 12.0 grams of aluminum. I really like this pictogram or figure from your book. Commit that to memory. You're starting with mass of A. So we've got mass of A. We've got mass of aluminum here. We need to now convert to amount of A in moles. So I need moles of aluminum. To get to moles of aluminum, I'm going to say 1 mole of aluminum divided by 26.98 grams of aluminum. That's the atomic weight of aluminum. I am now in moles of A. Now it tells me I need to get to moles of B. Okay, my moles of B here is my moles of hydrogen because that's what I'm trying to figure out how much I'm going to produce. So times 3 moles of H2 divided by 2 moles of aluminum. I got those numbers again from the balanced equation. 2 aluminums produce 3 hydrogens. 2 moles of aluminum produce 3 moles of hydrogen gas. Now I'm here, and now I need to get to mass of B. So I'm going to say times 2.016 grams, because it's H2, it's 2 moles of hydrogen, it's H2, divided by 1 mole of H2. Now, I said there's 2 main spots students will mess up. One spot is balancing the equation, the other spot is here. I highly, again, recommend, like we did in the last example, to go through here and show that your units are appropriately canceling. Grams of aluminum to grams of aluminum, canceled out. Moles of aluminum to moles of aluminum, canceled out. Moles of H2 to moles of H2, canceled out. I'm left with grams of H2, which is what I want. Remember, in order to cancel out, it has to have one in the numerator, one in the denominator. And this does not cancel out the numbers, just the units. Our numbers are still here. Go ahead and do the math here. And when I solve this out, I find the answer to be 1.34 grams of H2. So this means that 12 grams of aluminum will produce 1.34 grams of H2. So now we've gone all the way from grams of one to grams of the other. Another question here we have, and this is the last question in this video, what mass of oxygen gas is required for the complete combustion of 29.0 grams of butane, C4H10? First trick here is realizing that you know how to give me the balanced equation here. And in this question, you have to figure out your own balanced equation. We want to know mass of oxygen gas, which means grams, required to completely combust. We do know what that means. 29 grams of butane, which is C4H10. So it's telling me here, mass of O2 is grams, complete combustion. So I'm going to take butane, C4H10, and I'm going to react that with excess oxygen, because again, that is combustion, to produce CO2 and water. So balancing the equation here, carbons, hydrogens, oxygens, 4, 10, 2. 1, 2, and 3. Let's go ahead and put a 4 in front of the CO2. Now I've got 4 carbons on each side. Now I've got 9 oxygens on my product side, because 4 times 8 plus the 1. Next, let's go ahead and balance our hydrogen. We're going to leave oxygen for last because on combustion reactions, oxygen is the one that's a pain to balance. 10 hydrogens to 2 hydrogens. I'm going to multiply this by 5, giving me 10. Now that gives me 8 plus 5. That gives me 13 oxygens on that side. Now, my carbons are balanced, my hydrogens are balanced, my oxygens are not even close to balanced. So what I'm going to do is I'm going to go ahead and do, we talked about this in the combustion video, but I have 13 and 2. Easiest thing to do here is to give yourself a fraction, 13 halves. 13 halves of O2 is 13. Then what I'm going to do, I'm going to erase this because I want to check the answer to make sure. Sometimes combustion reactions can get messy. I'm going to multiply through the entire reaction by 2. So 2 C4H10. That will give me 13 O2, 8 CO2, and 10 H2O. Let's see if that's correct now. I've got 8 carbons, 20 hydrogens, and 26 oxygens. Here, 8 carbons. I have 16 oxygens here out of the CO2, 20 hydrogens, and another 10 oxygens, 26. It is now correctly balanced. So I'm going to rewrite that equation above because I'm going to need this space. I've got 2 C4H10. I know it's a liquid because butane is what it is in lighters and it's liquid in lighters. 13 O2, 8 CO2, and 10 H2O liquid. So now let's go ahead and write down what do we want to know. We want to know the number of grams of oxygen that we can produce. Oxygen gas, as we see here too, or oxygen gas required, we're going to consume. We see it here in our reaction, but we should also know that oxygen is a diatomic, so it will be O2. So number of grams of O2 that we're going to require to completely react 29 grams of butane. Write down what we're given, 29.0 grams of C4H10. So right now I'm here. I need to get to amount of A in moles. So 1 mole of C4H10 divided by the molar mass. The molar mass of butane, if you add this up, 4 carbons, 10 hydrogens, is 58.12 grams per mole. Now I'm here. Now I need to go ahead and use my balanced equation to convert to moles of B. In this case, B is what I'm looking for. It's O2. So times 13 moles of O2 to 2 moles of C4H10. Now I'm here, and now I need to get to grams of O2. 1 oxygen is 16 grams per mole, so 2 oxygens would be 32 grams per mole. Go ahead and make sure that everything is set up correctly and everything is going to cancel out correctly. What I mean by that is grams of C4H10 cancels with grams of C4H10. Moles of C4H10 cancels with moles of C4H10. Moles of O2 cancels with moles of O2, and I am given grams of O2. So I am getting to the point I want to be at. Next, go ahead and plug this in your calculator. And I forgot to write this one down, so 1 second. Okay, so what I find, the number of grams of O2 equals 104 grams. So it will take 104 grams of O2 to completely react 29 grams of butane. So in this one, you had to come up with the balanced equation, but again, you guys should know how to do this because you know complete combustion now. You had to come up with your balanced equation. Once balanced, you had to use it in your stoichiometry and figure out how many grams of O2 overall did you need to completely react 29 grams of butane.